Direct current motors. What we're going to look at in this presentation specifically is DC motors, different types, how they work. So let's get started. Remember, the parts of the DC motor and generator are identical. And so just as a quick review, we have the commutator, which was individual isolated sections of conductive bar that were connected to loops of wire that was wound on the armature. And then we had brushes that would connect to that. And the brushes would then be interconnected with one of two different types of windings. We have in here the stator of the motor, which we have a series or a shunt winding. All of it is connected together with a large metal frame that's used to align all the magnetic lines of flux. So this is what we're going to be looking at. Instead of a generator and a prime mover, now what we have is a motor and a mechanical load. And so again, we are converting energy from our electrical source into the motor to convert it to something called torque so that we can turn the mechanical load. This is really the same operation as a generator, the same animation and the same sort of rules that we're going to look at. And more basically, we're going to identify what happens in the system with a split ring rather than a commutator because it's much easier for us to interpret. So when we're dealing with motor action, it requires the use of the right hand. Right hand, just like the left hand rule for Fleming's induction of voltage, now we use a right hand rule. And the right hand rule now, the fingers indicate the same types of things, but instead of indicating what direction I'm forcing the conductor, like a generator, I'm indicating what direction the conductor is being forced due to the magnetic field. So you can see here with the right hand, the direction of field is always north to south. The current direction on the conductor is the middle finger, as well as the thumb indicating the direction of thrust. So this is sort of what we have. Remember that the armature or the DC motor is going to be connected to a source of electrical energy, which means that these two conductors here indicate or represent one winding inside the armature. They're energized with an external DC source, which is causing the current to flow through them in this direction that you see with the dot and the X. If we utilize the right-hand rule, in addition to the north and south poles that we see here with the magnetic flux, we can see that the thumb indicates an upward force with this conductor and a downward force with this conductor here. It's important to realize that the denser the magnetic flux is, the more force is applied. And rotational force in the world of mechanics and electrical rotating machines is called torque. And so that current value or that increased magnetic flux could be due to more current flowing in this conductor here in the loop, or it could be from this, my field coils that are mounted on the machine. So again, this just shows how the system is set up, whereby we have a applied DC source connected to our conductor, and that forces current through the conductor, and the current through the conductor establishes a magnetic field, and that magnetic field then interacts with the main magnetic field, the north-south here, and it causes a force to be applied on the conductor. And here's yet another example of such a device. So mechanical loads require a motor to apply torque to turn them. And the amount of opposition to the motor, and you can think of this as the difficulty the motor has in spinning the mechanical load, is called counter torque. So a pump or a mechanical load exhibits counter torque. And so the motor must be able to exceed that counter torque in order to turn the load. Now, of course, this is overly simplified. We all know that there are different things to be considered, such as inertia and starting a mechanical load from a standstill, which would require more torque to be applied. But that aside, the basic principle is that the motor would have to be able to deliver torque that is larger than the counter torque that is exhibited by the load. Another important thing is that a motor will always attempt to turn the mechanical load, regardless if it is capable of overcoming that counter torque. And to sort of provide an example of that, take this for instance, a motor with a teeny tiny little aquarium pump. Obviously, the motor is capable of turning that counter torque, and the motor will do so quite easily. However, what if I took the same motor and I connected it to a pump that was larger, like we had one pump for all of Comox? The motor is not smart. Inherently, a motor is quite dumb. And so the motor will try as best it can to turn that counter torque, which far exceeds its rating. And we'll find that there are some outcomes of this, and you can probably guess what's going to happen if you were to prevent that motor shaft from turning. What's going to happen to the current that the motor is drawing? It's trying to use tons of energy in order to turn that massive shaft, which it is completely incapable of starting to rotate. And so because of that, it's going to draw a significant amount of current. So DC machines, generators, and motors are identified in the same way. We have armature windings, series coil, shunt coil, and it's represented as A, F, and S. Throughout your ITA binder, there are lots and lots and lots of examples of connections. We're not focusing on the actual connections in the terminal box of the A, the F, and the S. What you do need to realize is a basic identification of the types of connections we have and what the ramifications are of using one over another. It's somewhat unrealistic to assume that any electrician is going out to the field to a 6-lead DC motor that could then perhaps be wired in one of 4 different orientations. So let's take a look at these general connections and how they work together and what the advantages and disadvantages are of each one. We have a series connection, a shunt, a cumulative compound, and a differential compound. The cumulative compound, just like the generator, has a short or long shunt application. And the differential compound connected motor, although it could be connected in short or long shunt, actually has no application whatsoever. So it's one that we'll take a look at. Why do we even, what is the reason for this motor? So we'll take a look at that at the end. When we're looking at the diagrams, it'll be interesting to note that although they do have the same identifier as in shunt generator and shunt motor, now what we're looking at is a difference in how it's sketched. In a generator, remember the source of a schematic is always at the top, and so the armature is seen as the source and it provides current down. And notice the current direction flow. In a generator, the current provided by the armature not only flows through the armature, but it splits and also provides current, or rather, I misspoke there. Not only does it provide current for the shunt field, it also provides current for the electrical load. And so you would have a circular path of current here, and then a splitting of current at this junction as it supplies the bulk of the current to the electrical load. On the right-hand side, we see a DC shunt motor. This is a little bit different. Source is at the top, electrical current comes down, and notice that the current flows through both legs in the same direction of this particular diagram. And so again, that's important to realize that the current flow is in the same direction through each device that we see. So let's take a look at the first one. This is called a series DC motor, and we can see that it's got one coil, a series field coil, and the series field coils in series with the armature. At no mechanical load, there is a low value of current due to a low value of magnetic flux, but it has an extremely high speed, as in dangerously high. And so this is something that's considered to be not beneficial. You would not want to run a series motor with no mechanical load. At full mechanical load, the magnetic flux increases, and that's because the current flowing through the coil has increased, and if we increase the current, we increase the magnetic flux. Due to this, we are going to get rated current flowing through the motor, and it's actually going to slow the motor speed to its rated value, or base speed is what we refer to it as typically. So a series motor has a very extreme graph that we see when it comes to current and torque, and also current and speed. At the very beginning, you'll notice very low torque, and then extremely high here. As we increase the load, we increase the torque. It's quite a steep curve. Here, this one, it starts extremely high speed, and then it drops right down to rated speed once we have rated mechanical load on it, right? So the rated mechanical load is what we're looking at. If you look at this diagram here, when you first start the motor, it would be a stationary position that the mechanical load is in. And so really what we would be looking at then is this dotted line would be like over here. It's a really large mechanical load because it's stationary. And what that means, if we look at the line here, is that the torque applied at start for a series motor is actually quite large. So it's got an extremely high starting torque, but its percent speed regulation is atrocious. Let's look at the shunt motor. This one has, again, a single coil, but the single coil is made with a much thinner wire, and it has many more turns, and it's connected in parallel with the armature. So at no mechanical load, we have a low current and slightly higher than rated speed. And that's because there is a defined value of current flowing through the shunt field, and that current value established by the ohms of the shunt coil would then dictate how much flux we have applied to the armature. Now it's going to be slightly higher than rated speed. When we're at full mechanical load, the magnetic flux remains unchanged. And that's because the ohms of the shunt field determines how much current flows through it, not the current of the load. And so most of this load current flows through the armature, or the current required by the motor to turn the mechanical load. And so what we would see is that the current will increase. The current value will increase, it'll go up to rated current, and the speed will decrease, just not as severely as what we saw in the series motor. So now we're hanging out at 1800 RPM. If we look at the graph for this, the speed, you can see it starts off very high, like pretty much at rated value, so not dangerous at all. And then it drops a little bit once we hit rated value, and if you were to increase the mechanical load, it would droop even further. If we look at the torque, although it is an increased value, it's quite a linear line, this is something that does not reach the same height as the series. The series motor had a much higher peak value of torque all the way over here on the right-hand side. And so a shunt motor won't have as good a starting torque, but its percent speed regulation is way better. Now, something funny happens with a DC motor. You can adjust the speed, as we had discussed in the previous presentation briefly. You can easily adjust the speed of a DC motor, and especially a shunt DC motor. And that's simply by adjusting the amount of current in the shunt field. If I decrease the current in the shunt field, that means that the counter EMF applied to the armature is going to be changed. And so that will cause us to have a faster motor. So as we decrease current in the shunt field, the motor speed increases. If we were to increase the current in the shunt field, that would cause a situation where the speed of the motor would slow down. So as we see here, increasing the shunt current, so the shunt field current, will cause the motor to slow down. If we decrease the shunt current, the motor will speed up. Interestingly, if you were to decrease the shunt current to 0, as in we were to cut this in half or increase the ohms to its maximum value, the speed of the motor will increase to a dangerously high level, and it's considered a runaway condition. So not something we want to do. Let's look at a compound motor or cumulative compound motor. A cumulative compound motor has 2 windings, and the 2 windings ensure that we have the best of both worlds. We have the best of the shunt, and we also have the best of the series motor. The current in both the series and the shunt are traveling in the same direction, which means that the magnetic flux is aiding one another. It's not in opposition. We have a long and a short shunt connection, and again, short shunt means that it's only in parallel with the armature, whereas long shunt would be across the entire circuit. Again, I don't want you to memorize all of the connections here, because that is, at least for electricians in this generation, not important. But what you should be able to recognize is the difference between a long shunt motor connection and a long shunt generator connection, and the difference simply between a long and a short shunt diagram. If we take a look at the cumulative compound motor graphs, we can see speed of series and shunt, and then here's speed of the compound. So it's sort of in between the two. And then torque, we see torque really high for the series and somewhat subdued for the shunt, but look, the compound is in the middle. And so the cumulative compound DC motor is considered to be the best of the 2 different applications. It's sort of the general use or general workhorse, you could say. Again, we could have the same speed control features. It's always in the shunt field. Let's look at this odd duck. This is called a compound motor, but it's connected as a differential. Now, why is this, I would say it's arguably a rather odd topic to even have significant content in your binder regarding, but I want you to look at this, the bottom. Not so much all of the individual connections, but look at the current here and here. They're in opposite directions. And what that means is that they will generate flux values in opposition to one another. And this leads to a very interesting outcome. So first, when we first start the motor with no mechanical load, the shunt field will generate more flux than the series winding. And because of that, the motor will spin in the direction associated with that shunt flux. So in our example here, the yellow arrow is showing that it's traveling in a counterclockwise direction. As mechanical load is increased, though, the series field magnetic flux will also increase. And that's because the current that's demanded by the mechanical load in order to turn this thing will increase. But the current through the shunt field will not, because the shunt field ohms is set. So as we increase mechanical load, the current that the motor draws increases, and that increases the magnetic flux generated by the series coil. Now, at a certain point, either due to just steady increase in mechanical load or due to the motor becoming overloaded, the series field flux will exceed the shunt field flux. And remember, they're in opposition to one another. And what that means is that once the series field flux exceeds the shunt flux, the armature, well, the armature is now going to react or associate its direction with this opposite, larger magnetic field. And so what that means, the motor instantly changes speed, or rather changes direction at full speed. This is considered bad, as you can well imagine, because it would be difficult to pinpoint exactly what point would this happen. And so I would say that overall, a compound motor connected as differential would be a completely useless and dangerous connection for a DC motor. A great example of this is more so seen in accidental connections. Accidentally, a DC motor being connected in differential as opposed to cumulative. Let's take a look at this video. This is of a ski lift in Georgia. And the ski lift, or at least a lot of different ski lift types of equipment, operate with large DC motors. Now, I don't know all of the background on this particular instance, but it does seem probable, based on the footage we're going to view, that this accidentally was connected in differential. Let's take a look. It's going at full speed in the opposite direction. Yow. That's pretty scary. I mean, honestly, that is not something you would want to be involved in. And of course, it's somewhat uncontrollable. You would have to then shut down the main power to the motor. And for reasons unknown to me, that was not an action that the operators were able to do. So, moving on, when a DC motor is turning a large mechanical load, such as something like this, and then going to, instead of pumping water, maybe we're pumping muck. What's going to happen to that motor current? Well, the motor current is going to increase, and that's because we need more electrical power in order to generate more mechanical power, which is then converted to torque. So if you need more mechanical power over here, you need more electrical power coming into the motor. And because of that, we again get that neutral plane shift that we had discussed with generators. The main difference that you'll see is that the shifted neutral plane, as we increase the load of a DC motor, it will shift in the opposite direction to the rotation of the motor. So it's a little bit different from a generator. And so we can again see the arcing that could be established on the brushes, and that could cause damage to the actual commutator and reduce the torque. How do we prevent this or solve the problem? Same as on a generator, we have interpoles and we also have compensating windings. So that brings us to the end of our presentation on DC motors. Be sure to check out the other presentation on calculations involved in DC motors.